Data structures and algorithms form the foundation of computer science and software engineering. Understanding these concepts is essential for creating efficient, scalable software solutions. A data structure is a way of organizing and storing data in a computer so that it can be accessed and modified efficiently. Think of it as a container that holds your data in a specific arrangement. Here are some common examples of data structures. Arrays store elements in a sequence, like books on a shelf. Stacks work like a pile of plates where you add and remove from the top. Trees organize data hierarchically, like a family tree. Now let's define algorithms. An algorithm is a step-by-step procedure or set of rules for solving a specific problem or performing a particular task. Here's a simple algorithm example: making a sandwich. Step 1, get bread. Step 2, add filling. Step 3, close sandwich. Each step must be followed in order to achieve the desired result. Why is analyzing data structures and algorithms so crucial? The choice of data structure and algorithm directly impacts the performance, scalability, and efficiency of software applications. Let's illustrate this with a classic example: searching for a name in a phone book. We'll compare two different approaches and see how algorithm choice dramatically affects performance. Linear search checks every entry one by one from the beginning until it finds the target name. This approach is simple, but can be very slow for large phone books. Binary search, however, takes advantage of the fact that phone books are alphabetically sorted. It repeatedly divides the search space in half, making it much faster for large data sets. The performance difference is dramatic. For a phone book with 1 million entries, linear search might need to check up to 1 million entries, while binary search needs only about 20 checks. This demonstrates why choosing the right algorithm is crucial for building efficient software. This introduction shows why understanding data structures and algorithms is fundamental to computer science. The right choices can make the difference between software that's fast and scalable versus software that's slow and unusable. In the following sections, we'll dive deeper into analyzing and measuring these performance differences. Asymptotic analysis is a fundamental method in computer science for describing how algorithms behave as input sizes grow very large. It helps us understand the limiting behavior of functions, particularly algorithm runtime. Big O notation is the standard mathematical notation used to express the upper bound of an algorithm's growth rate. It describes the worst-case scenario, the maximum amount of time or space an algorithm will need. There are two main types of runtime analysis. Worst-case analysis provides a guarantee. It tells us the maximum time an algorithm will ever take. Average-case analysis gives us the expected performance under typical conditions. Now let's examine the most common Big O complexities. O of 1 means constant time. The algorithm takes the same time regardless of input size. O of log n is logarithmic, very efficient. Doubling input size only adds one more step. O of n is linear time. If you double the input, you double the runtime. O of n log n appears in efficient sorting algorithms like merge sort. O of n squared is quadratic. Doubling input quadruples the runtime, making it inefficient for large datasets. This graph shows how different complexities scale with input size. Notice how constant time stays flat, logarithmic grows very slowly, linear grows steadily, and quadratic grows rapidly. Understanding these growth rates helps us choose the right algorithms for our problems. We begin with heaps, a fundamental tree-based data structure that maintains a specific ordering property called the heap property. A heap is a complete binary tree where each parent node is either greater than or equal to its children in a max heap, or less than or equal to its children in a min heap. Heaps are primarily used to implement priority queues, where elements with higher priority are served first. The main operations are insert, extract, maximum or minimum, and peak, all with efficient time complexities. Now let's clear this and move to hash tables, which provide a completely different approach to data organization. Hash tables implement associative arrays, allowing us to store key-value pairs and retrieve values using their associated keys in constant average time. A hash table uses a hash function to compute an index into an array of buckets or slots, from which the desired value can be found. Let's see how keys are hashed. The key apple might hash to index 2, while banana hashes to index 5. The hash function determines where each key value pair is stored. Hash tables support fast operations with average case constant time complexity. However, collision resolution is crucial when multiple keys hash to the same index. Let's clear this and examine our final data structure, disjoint sets, which solve connectivity problems efficiently. Disjoint sets, also known as union-find data structures, efficiently manage a collection of disjoint sets and support two primary operations: union and find. Initially, we have separate elements, each in its own set. The find operation determines which set an element belongs to, while union merges two sets together. When we perform union operations, sets merge together. For example, union of sets containing 1 and 2 creates a larger set, and union of 3 and 4 creates another set. Disjoint sets are particularly useful for network connectivity problems, such as determining if two nodes are connected in a graph, or for implementing Kruskal's minimum spanning tree algorithm. These three data structures, heaps, hash tables, and disjoint sets, each solve different computational problems efficiently. Understanding their properties and time complexities is essential for choosing the right data structure for specific algorithmic challenges. Implementation choices can dramatically affect performance, even when algorithms have the same theoretical complexity. Consider hash tables. The choice of hash function can make the difference between excellent and terrible performance. Different implementations of the same data structure can have vastly different performance characteristics. Binary heaps and binomial heaps both provide logarithmic operations, but their constant factors and specific operation costs vary significantly. Even when algorithms have identical big O complexity, constant factors and lower-order terms can create significant performance differences in practice. A algorithm with complexity 100n might be slower than one with 2n squared for reasonable input sizes. Making informed implementation choices requires understanding the underlying principles of data structures and algorithms. Consider your specific use case, expected data patterns, and performance requirements when selecting implementations. Empirical testing and profiling are essential to validate performance assumptions. Theoretical analysis provides guidance, but real-world performance depends on many factors, including hardware, compiler optimizations, and actual data characteristics.